I want to work a couple of story problems from section 5.4, and both of these story problems are just like the ones in your homework, and these problems are examples of solving an equation where the variable we're trying to solve for is in the exponent, and we're going to use logs as a way to solve these equations. First one I'll do is number 63, so this is once again section 5.4 from your book, and number 63. So, let's let this thing focus. Sort of slow. All right. So if I read the problem, it's called U.S. population growth. The population N of T, let me write as we go. So N of T, where N is the population of the United States, T years, so T is the number of years after 1980 may be approximated by the formula N of T equals, so here's the formula, 231 e to the 0.0103 t. When will the population be twice what it was in 1980? So it's almost like the starting point for this equation let me put it this way. T equals 0 when the year is 1980. So it's like everything is going to be based off the year 1980, which we're going to consider year 0. T equals 0. So therefore, if we were to think of 1985, for 1985, T would be 5. For 1992, T would be 12, okay? So you understand now how the T is going to work. Now we're going to solve for that T. We're going to see how long it has taken for the population to double. Now what's interesting, this equation here, we've actually seen before. That's just a natural exponential equation. It's the kind of equation that we looked at in section 5.3. And so since our exponent is positive, this is a growth equation, so this equation is growing. Now what's interesting is it's asking me, when does the population double? If I want to see when does the population double, I need to determine what the population was at the beginning. So when T equals 0, if I plug T equals 0 into this equation, I'll have N at times 0 equals to 231 e to the 0. And e to the 0 is just 1. So the population in 1980 is 231 million. So they're asking me, how long will it take for the population to double? So if the population is going to double, that means it's going to be twice of 231, which is 462. So therefore, I go back to my equation, and I put in, for N of T, 462 equals 231 e to 0.0103t. So this is the equation I'm going to use to determine when the population doubles. So once again, the initial population in the year 1980 is 231. When it doubles, the new population is 462. And when I solve for t, it's going to tell me how long it would take for the population to double. So here's my t I'm trying to solve for, and it is stuck in the exponent. So how do I get at it? I use logs. Now whenever you're trying to get at the variable in an exponent, the first thing you have to do is get the exponent by itself. Right now the exponent is not by itself. I've got this 231 multiplied by the exponent. So I'm going to now divide both sides by 231. Now the left-hand side just equals 2, and the right-hand side equals my exponent. And at this point now, I want to show you two different ways using logs to solve for this t. I'm going to tell you the way that I prefer, because to me it seems faster and it's almost like a shortcut. But I also want to show you the way that we talked about in class when we first began to introduce logs. So if you recall, the two key equations for logs are, we have the log equation, and then we also have the exponential equation. And we learned how to go back and forth. So what I can do to solve this, I right now have an exponential equation. I can take this and convert it into the log equation. So I'm going to go ahead and do that. I'm going to figure out my x and my y and my a. So I'm going to take my exponential equation and figure out the x and the y and the a. So in this case, my x is 2, my a is e, so that's the base, and then my y is going to be my exponent, 0.0103t. And with that information, I can now plug the x and the y and the a into my log equation, and I will have 0.0103t equals log base a. I could write log base e, but log base e is actually natural log. So let me just go and write natural log of x, and x is 2. So you can see how, by using the definition, by using the logarithmic equation and the exponential equation, I was able to convert this from an exponent to a log. And the beauty of that is, now look, there's my variable t, which I can now solve for. By converting this into a log equation, I now can get at my t, I can get at the variable and solve for it. As a matter of fact, if I just divide both sides by 0.0103, I get natural log of 2 over 0.0103, and then I simply grab my calculator. Hopefully by now you all have lots of experience in how to do these kinds of calculations. So 2 and then the natural log divided by 0.0103, and I have 67.3, so actually 67.3 years. And I want to make sure I answer the question. It says, when will the population be twice? Well, I have to add 67.3 to 1980. So the actual year when it doubles will be 2047. Does it tell me to round? Let's just leave it a year. 2000, around 2047. So you see, there's an example of, I had an equation where my variable was up in the exponent, and the only way I was going to be able to solve for that variable was to turn it into a log. Now I want to show you a second way. I'm going to start with this equation right here, and I'm going to solve it again, but I'm going to do it in a different way, and what I think is an easier and faster way. And of course, it's up to you which one you prefer. Both of them will give the same answer. So here's my exponential equation. And let me remind you of one of the rules that we learned about when we start talking about logs. And it's this rule. It says, if you take log base a to the x. So in other words, what's going on here? We're taking log base a, we're taking the log of a term that has an exponent, and the base of the exponent is a. So you notice that the base of the log and the base of the exponent are the same. You know what that equals? X. It just equals the exponent. So how does this apply to solving this problem? Well, let me do a quick, simple example so you can understand. What if I was trying to solve seven t equals what? My variable is up in the exponent. Since actually, let me assign a number here just for fun. 7t equals 5. I'm trying to figure out what does t equal. Well, how do I get at that t? One of the things I can do is, you notice if I take the log base 7 of both sides of this equation, which I can do since I'm doing the same thing to both sides. Look at the left, log base 7 of 7t. That's my rule. What does that equal? It just equals the exponent. So now I have solved for the variable. I'm going to use that same principle now back for my exponent here. Of course, my base is e. So when my base is e, I'm really talking about log e. Of course, we don't call it log e. We call it natural log. So I'm going to take the natural log of both sides of this equation. So natural log of 2 equals the natural log of e to the 0.0103t. Now the right-hand side, because I'm taking the natural log of an exponent with a base of e, it just equals the exponent. And now if I solve for t, I have the exact same thing that I had a few minutes ago. Now, in my opinion, this to me is simpler. I prefer it. The previous way, you had to figure out your x, figure out your y, figure out your a. You had to write down your two sort of equations here. I just look at the base of my exponent. That tells me what kind of log I should take on both sides. I take the log of both sides, and then boom, I'm pretty much done. Now let's do a second problem out of section 5.4, number 66. This is a continuously compounded interest problem. Now before I read the problem, once again, I'm going to refer back to section 5.3, and we have an equation that tells us how to calculate the compound interest, where P is the amount of money you put in the bank, R is the interest rate, and T is the number of years. Once again, this is the equation when you have continuous compounding. So it says, if interest is compounded continuously at the rate of 6% per year, so my interest rate is 6%, approximate the number of years. They're asking us to find the number of years it will take an initial deposit of $6,000 to grow to $25,000. So they're going to put $6,000 in this bank. They want to know how many years it would take for the money to grow to be worth $25,000. So I'm just going to plug all the information into my continuous compound equation. So the A is 25,000. The P, the initial investment, is 6,000. E to the R, now once again, 6% interest rate translates into a decimal of 0.06, right? So this is 0.06T. I need to solve this for T. So here we go again. The variable I'm trying to solve for is in the exponent. I'm going to use logs to get at that T. And in this case, I'm going to use the little shortcut method. But remember, the first step is you've got to have the exponent by itself. So the first thing I have to do is to divide both sides by 6,000. And therefore, I now have the exponent by itself. And now, since my base is E, I realize, you know what? If I take the natural log of both sides of this equation, and on the right, now we apply our special rule that says you're taking the log of an exponent and the base of the log and the base of the exponent are the same. It just equals the exponent. So the right-hand side is 0.06T. The left-hand side is this natural log of 25,000 divided by 6,000. I can finally solve for T, the natural log of 25,000 over 6,000 divided by 0.06. And once again, now I have to grab my calculator, and I take 25,000 divided by 6,000. Then I take the natural log of that and divide that by 0.06. And I end up with 23.8 years. So it looks like it would take almost 24 years for the money to grow from $6,000 to $25,000. So there are a couple of examples where you have story problems and the variable you're trying to solve for is in the exponent. And we use logs to allow us to solve those equations.